Hi, it's Bruce again, and welcome to my Colorado Rocky Mountain lab. And today we are looking at a Wavetek Model 114 function generator with sweep and voltage controlled generator. This is a complex little unit. Does a whole lot, sort of like a Swiss pocket knife, if you would. This will cover a range from 0.0015 hertz to a megahertz. It does that in 8 ranges, and then there are 2 more ranges selectable from a top range switch too. You can go times 0.3 or times 1. We have a large graduated dial, the major divisions from 1 to 10. So if I was in the times 1 position, which I am right now, and I am on 1 in the major division, and I am on 0.01 as I am then 1 times 0.01, or 0.01 hertz. And then as I raise it to 10, I would go up to 0.1 hertz. 10 times 0.01 is 0.1. And then you can, if you were to look at the screen of my oscilloscope right now, you'll see that that line is very slowly rising. I can make it rise faster by turning the major frequency dial, which I just did. I raised it to 10. And you'll see that we are going up and down very slowly, and I can take that down to 1/10 of what that is, and then divide that by 3 by turning this major range switch and take the dial down to 1, and that line will appear to almost not be moving at all. But if you sit here long enough, you will see that it is. Anyway, 0.0015 to a megahertz. Okay, then we have triangle waves. We have 2 different triangle waves. They are 180 degrees out of phase, as we have 2 sine waves 180 out of phase, and then we have square waves the same thing. In addition, we have a sine wave that is above the 0 line, so we've offset it by a positive voltage so that the entire sine wave is positive. That's all switch selectable by this back switch, which right now we are on sine, and doesn't matter which one, but you can go 180 out of phase at just by switching the main switch. Let's put ourselves at times 1, something that we can readily see. Let's go times 1,000. We see on our oscilloscope now that we have a waveform that is recognizable. That's 1,000 hertz. And as I raise the main dial, we can see that we will go up to 10,000 hertz. We can go down to a triangle wave. And again, raise or lower. And you can see the triangle wave. Or switching all the way to the right, we have a square wave. And taking ourselves from a low frequency of around kilohertz up to the 10,000 hertz. All right. Here, by the way, would be the sine wave above 0. You ought to be in the DC mode to see this. If you put it in the AC mode, it's just going to center the signal about the center line. You won't be able to see it. Okay. And then this is our center dial, is our amplitude for all of the waveforms. As I dial that in, the amplitude changes. Okay. Let's put ourselves, we have an internal sweep on this. I am on continuous right now. I'm going to choose to put myself center of the dial just for convenience. And then I'm going to take my my sweep rate dial, I'm going to put it ×1 and turn this thing up so that we can see it. Now this dial over here is our vernier for sweep bandwidth. I've turned it off so that we are getting a steady signal. If I turn it on, we're going to start to see that that signal up there will start sweeping. And as I control my sweep rate with this dial here, you'll see that sweep rate up there change. I just lowered my starting sweep so we can see it easier. Moving ourselves back to 5, changing our range on the scope so that you can see that more easily. So we can control our sweep rate. This is, if I rotate all the way to the right, that says sweep the entire dial to the maximum magnitude. If I put it all the way to the left, it says give me what the dial is reading, whatever it is. So this is like the sweep bandwidth in between that dial setting and maximum. We can also choose to sweep and hold by switching this dial to sweep and hold. And I look up at my signal up there and I see that it's steady. And I have a switch down here, and I can reset the sweep, and I can trigger it by pushing up, and I'm going to do that while you look at the screen. We're pushing up now, and there's our sweep to the maximum. Or we can go trigger gated, where we feed a trigger signal in here, and we cause it to sweep. I'm going to go back to continuous. Very handy little device to have. Another thing we have is a voltage control generator input, and we're going to discuss that momentarily. So this unit is in really nice condition. Got a beautiful cabinet, nice aluminum front panel with knobs. This unit was made in San Diego by Wavetek Corporation. We have a front output for all of the functions. We have an input for the voltage control generator. We got a trigger input. And if we turn this whole thing around, we have a barrage of outputs on the back here. Here is our multiple output, and if you select on the front to have a sine wave that is, we'll say at 0 degrees, then the sine wave that comes out of the back of here will be 180 out of phase. Same thing for any of the other waveforms. So it just chooses the opposite phase. Here we have the sweep output. We have triangle output. We got a sine wave output, square wave 5 nanoseconds, square wave. This would be the, I think it's 20 nanoseconds. An offset and a sync input. There's a 0 adjustment back here. So we're going to run this thing through some demonstrations just to kind of give you a feel for it, maybe get you a little excited about it, as I am. So bear with me. Okay, so we've hooked up a 455 kilohertz ceramic resonator. That's this little orange thing. We've got it hooked up in series with the signal source. So we're coming out of the signal source, say coming through the ground, going through the ground to the probe, up to the scope. Then we're coming out of the scope and coming through the probe to one side of the ceramic resonator, and then we're coming out of the other side of the ceramic resonator and running to a 50 ohm, 56 ohm resistor which is connected to the other side of the generator. So we've got a resistor and a 455 kilohertz ceramic resonator in series with the scope and the signal generator. And we're sweeping. And what we should see, okay, so now we can see the resonance signal of that 455K ceramic resonator. We've got the sweep generator starting at about 400K and ending at about 500K, and that gives us the best picture of this thing, and it goes under resonance quite heavily. We are right now at 0.2 volts per division, so I'm going up 0.2468. So that's about 1.6 volts peak to peak. It's pretty dramatic. And we're less than well, when it's at the no resonance point, which is just to the right of that curve there, we're not talking a tenth of a volt, so really interesting looking figure. And made watchable by the sweep generator, so one of those little interesting experiments I like to produce. Alright, we'll move on. Okay, so now as I dial to 0.5, excuse me for bumping the cord here, I'm going to dial to 0.5. You can see the speed pick up quite a bit. Let's go to 5 hertz. All right. Let's go to 50. Okay. And if you'll pardon me, I'm going to go back into AC. We'll keep ourselves symmetrically around the 0 line. And we'll go to 500. $5,000. We'll step up our horizontal sweep rate so we can keep up with this thing. There is 50,000. And 500,000. And again, we've got to step it up in order to see the waveform. But there we go. And I could turn it to triangle. There's a triangle wave. And we'll step ourselves back down to 50,000. $5,000, 50, 5. Yeah, we could go square wave if we wanted, just so we can show you that. There's a square wave at 50,000. And there'd be one at 500,000. 50, here's 5. Can't even see the whole thing without stepping down. So we've got a remarkable little unit that seems to do just about a little bit of everything. We're going to hook up the voltage controlled generator here in a minute and take a look at it. Okay, so we got the 114 set up right now to produce about 5,000 hertz center frequency. We're not sweeping it internally, we're just producing the 5 kilohertz, but we are putting a signal in on the voltage controlled generator input. And that voltage is coming from another generator up here, and I'm producing about a 5 hertz signal right now, and am producing an output that I'm using to drive the voltage control generator input, and that in turn is causing a sweep. Now, let me demonstrate that. I'm gonna turn my voltage down on this generator, and you see that my sweep has decreased. If I turn it back up again, okay, we get a significant sweep. And if I change my frequency, I'm gonna rotate this dial. Let's say we go to 6. We'll see it pick up. I'm going to turn it back down to 5, then to 4, and down lower. There's 1. 1 is on the dial, and we see that we're slowed up. And as I speed up, I'm back up to 5 again. You can see that we are modulating the 5 kilohertz signal by 5 hertz, and the degree of the modulation is dependent upon the voltage applied. I can cut the voltage down or turn it up and sweep it more. So that is an example of the voltage control generator doing modulation. Okay, so we're still at the 5 kilohertz center frequency, and we're just producing a steady tone right now, as you can see on the scope. But I now have myself connected to this ramp generator. And what I'm going to do, I can with this ramp generator provide either a DC voltage, they call it bias, or I can produce a ramp of an amplitude that's selectable anywhere in the range I want. Now I'm looking for 0 to roughly 5 volts. That would be the maximum, and that would cause a swing, a full swing across my my dial, taking me from my lowest capable up to my highest capable signal frequency. So let's give a demonstration of that. Let's go ahead and choose the bias, and I'm going to turn my bias up. And the way this thing is arranged right now, it's 0 to 1,000 on here, but it's divided by 100, so really it's 0 to 10. Mid-range would be about 5 volts, and I'm going to take myself up to just under the 5 volt range. And as I do that, we should see that we have produced a shift in frequency. I'm going to connect myself up again. Frequency went up with that 5 volts and then down. Now, if I lower my center frequency all the way down, okay, let's go ahead and that's my lowest, cleanest frequency. This is on the 1 kilohertz dial. I'm going to go ahead and hook up the 5 volts, and there you see we've swung all the way up to about 10 kilohertz just with the application of that voltage. Now if I turn that voltage down, you're going to watch it swing towards the 0 in frequency. All right. Up and down. So that's how you modulate it with that voltage. Now, if I was to use the ramp, I can literally sweep this thing. And there we go. I'm making a ramp of 0 to 5 volts and sweeping from I know, something less than a kilohertz, probably down around 2. Okay, so right now I'm producing a cycle in roughly 1 division, and I'm at 2 milliseconds, so I'm producing roughly a 500 hertz signal. Then, as I turn up my voltage, my bias voltage, I increase my frequency to some maximum. Okay, so with my bias turned up to about 0.5, well, it'd be 5 volts. My frequency is right now coming out at 1 cycle per division, and I am at 0.1 milliseconds. So we're getting 0.1 milliseconds, that's 10,000 hertz. So our maximum frequency at 5 volts is 10,000 hertz. And our minimum frequency at 0 volts was about 500 hertz. So we're going from 500 hertz to 10,000 hertz using 5 volts on the voltage control generator. That's a 20-to-1 sweep for 5 volts, which is what I have in the literature for this as well. So it's good to see. And then if I produce my ramp, I'll turn all that bias down. If I produce a ramp going from 0 to 5 volts, we should see our frequency sweep that entire range, 500 up to 10,000. Here's the 500. Here's the 10,000. So there's the voltage control generator demonstrated. I thought this was interesting. How many times have you seen 4 simultaneous waveforms out of a unit at the same time? This unit can produce 9 signals at the same time. Not that you'd want to see all 9 of them at the same moment, but you could want to see 2 or 3 of them for certain. Very interesting. This is from a lot of it from the back panel, and you may or may not need to use some attenuation in order to get it on your oscilloscope, depending on what scope you're using. Okay.